start video recording?
I did.
Okay, once more, remind me again your name, BRB. Why you are writing this strange code? I guess you are born in. You are?
No, I'm Peruvian as well, but this is my personal email. That's why it has this strange code. I would like to change it, but I don't know how. I don't use Microsoft Teams.
Okay. Anyway, your first name is?
Bruno.
Bruno. Okay, I will try to remember. Okay, and you were born in 1999.
That's correct.
Madonna. I am becoming very old if my students were born in 1999. Mm-hmm. Okay. Now, what is peculiar of this master is the fact that we are managing to establish a curriculum in which the courses are integrated. So we have courses which are one coordinated with the others. Now, this integration is even stricter. With these 5 courses, the first 4, Professor Giorgio and myself, we are responsible of these first 4. So we share the job in all these 4 courses, while dynamics of structures is held by Professor Alaggio. I will add Professor Alaggio in the chat of this team. Okay, you will find in the files Craig, the textbook of this course, and you will find the detailed program for dynamics of structures with the title of the chapters and sections of Craig, which are the program of the course. Okay. While for these 4, you will find a book which includes 90% of the subject, but much more. This book is written by as editors myself and Professor Stegman from Berkeley. You will find also in the files, and we will video record the lectures, okay, and we will try to upload these lectures in the YouTube channel of M&MoCS Center. M&MoCS is Mathematics and Mechanics of Complex Systems. Okay. So I think that this integration is very useful. Why? Because we try to avoid repeating the same things in different courses first, and then we will try to find a logical order in the subject, so that we try to organize it in the most efficient way. Okay, of course, you need to exert abstraction. So what you need to do, you need to formulate general theories, and then, in these general theories, abstract properties in common with different models are treated. And then, starting from the general theory, you particularize to specific theories. Okay. This we will try to do in particular. We'll start doing it today, because today we will discuss about discrete models of Lagrangian type. Okay, or if you like, Lagrange discrete mechanics. And then we will discover that maybe here we can place physics or even models. Okay, I want to show you how general is the theory developed by Lagrange. Okay, it is very general, and I will try to give you an idea of how wide is the possibility of application of this abstract way of formulating mathematical models. And how wide is the potential application of this theory. So you will need to suffer a little bit and trying to understand the mathematics behind these models. Then, and this is the reason for which I'm starting now, then you will go to dynamics of structures. Okay. By the way, even if he's not here, I will add to this team Dr. Erden Yildiz Dag, if I remember well his family name. Okay, who is assistant professor with us, and he will help you in reading and understanding dynamics of structure. Then you can meet Professor Alaggio. We will fix some dates, and then we can also try to get the help of another assistant professor who is in this moment in United States, but he will be back in 3 weeks. Okay. So my idea is to formulate a general, let us call it meta theory. So we try to formulate a theory which teaches us how to formulate theories. Okay, and this is Lagrange discrete models theory. Okay, and then after we have formulated this general meta theory, we will apply it to several. We will apply it to formulate specific theories. Now, as I told you, we wanted to have this course, we wanted to organize this master program in order to not only allow you to have a general understanding of mathematical modeling, okay, but also, as not everybody among you will have a scientific career, we wanted to have you in the situation to get the professional engineering certificate from European Union, okay? So you will, after this course, you will be allowed to pass the exam for becoming a professional engineer. Why I'm telling you this? Because your qualification will meet the standards of Bologna Agreement concerning civil engineering, but in Italy you can apply for every specialty in engineering for becoming professional engineer. Okay, so the specific theories which we will consider are mainly from civil engineering, and therefore dynamics of structures here plays a role. Okay, so I try to give you a clear order of the logical development of what I'm telling you. Lagrangian discrete models are very general. Okay, I will give you examples from economy. Okay, so we can invent Lagrangian models using the meta theory which I am describing you. We can invent, and I even wrote papers. So if you like, I can share with you these papers if you are curious about this. Okay, I wrote papers about applications of Lagrangian mechanics to economy. However, as the specific applications you must learn in order to be allowed eventually to get your professional engineer certificate, must come from the dynamics of structures. Okay, so I don't want to close your eyes, making you believe that the only application of this meta theory are in civil engineering. Okay, and there is only one way for doing this: showing you the most abstract theory and showing you also different applications. Few, but this is very important. Okay, now just few informations about Lagrange. Lagrange was actually Italian. Giuseppe Luigi Lagrangia. You know, Lagrangia is the place where you store corn in ancient Italian, and Lagrange is the same object in French. Lagrange started working in Turin. Then he got a position in Berlin where he stayed 20 years. Then he moved from Berlin to Paris. And as he was a clever man, Lagrange invented, okay, maybe it is too much. We say developed in the modern form the methods of optimization. Which is also very important in engineering. if you want to build something in the best possible way, okay, you need to find a function which must be maximized. Okay? Because you want to get that something, optimizing means that you want that something is the best possible under your building conditions or under your constraints if we are dealing in a more general setting. Lagrange is a person whose life is proving me how stupid I am, because he invented the mathematics which I will show you now and which usually requires some weeks or maybe months for being understood at the beginning of our career, when he was 17 years old. Okay. But not only he was very clever, but also he was very adaptive. So being in Turin, he behaved like an Italian. Being in Berlin, he behaved like a German. Being in Paris, he behaved like a French. He went through the monarchy, the absolute monarchy of Louis XIV, Le Roi Soleil, the god, the Sun King, okay, who was his witness at his marriage. Then he became a revolutionary, and he passed through revolution without being killed. Then with Napoleon III, he became senator, and he managed to be buried in Pantheon, the first Italian born person being born in the Templum of Franz big man. Okay, so this man managed to apply his optimization theory also in life, and this is what I invite you to do. Okay, so not only you will learn some mathematics, but if you are clever enough, you will not do what I've done when I was young, that is stupid, useless battles. Instead, you will optimize your actions for becoming, for getting the optimal configuration in your system. Why, when I wrote invented, I changed my mind, and then I wrote developed in the modern form the method of optimization. The reason for which I changed my mind while I was talking is the following one. In Hellenistic science, we will have some 8 hours of lectures about some ideas in epistemology and history of science directed towards mechanics and continuum mechanics. But now I want to tell you that in Hellenistic science, where, for instance, you know, Euclid and Euclidean geometry were invented in Hellenistic epoch. Hellenistic epoch is an epoch about 3rd, 2nd century before Christ. In Hellenistic science, many optimization problems were solved. Okay, one problem was given a planar shape, a polygonal shape, to find the shape in which, given the perimeter, one has to find the maximal area. This is the prototype of an optimization problem formulated with modern scientific methods. Okay, so given the perimeter of a polygonal shape, one wants to find the maximal area, the polygonal shape having the maximal shape area. Okay. Now, this problem has been already solved using the methods of Euclidean geometry. And the solution is, of course, I cannot draw an hexagonal shape, but the solution is an hexagonal shape with equal sides. And this is the honeycomb shape. So these Greek scientists said that probably bees in their evolution had managed to optimize the amount of honey which can be stored in a box having flat sides. Okay, so this optimization problem, this is the reason for which I cannot say that Lagrange invented optimization methods. He developed in the modern form the methods of optimization. Why? Where Hellenistic science stopped? There is a famous problem which is called Dido's problem. You know, Dido was the famous queen in the founder of Carthago, the mythological founder of Carthago. And the story, you know, Punic people arrived in the northern shore of Africa from Lebanon, and they wanted to establish a new colony there. And then they developed Carthago, which became the most powerful city in the Mediterranean Sea before Rome completely destroyed it. Okay. Now, if somebody among you may believe that they have nothing to do with Carthago, I will tell you that in South America, the DNA tests have found some genes coming from the Carthago pool of genes, so that somebody believes that the sailors, the famous sailors of Carthago, may have reached South America. But okay, this is not yet fully proved. What is the Dido problem? Okay. Given, okay, to find a closed regular curve. Okay, having the maximum area with a given perimeter. So we must understand what we mean with regular. Okay. And then, given a curve, okay, we need to find its shape among the set of curves having a fixed perimeter, which encloses, it has to be a closed curve, which encloses the maximum area. Okay. This problem could not be solved in the sense that Hellenistic scientists knew the result, but they could not prove mathematically. And the proof of this problem has been obtained as a simple application of Lagrange method. Okay, so this terrible problem, for Hellenistic scientists became a kind of homework for students when using Lagrange optimization method. Okay. By the way, you can conjecture that the solution of this problem is a circumference. Okay. And indeed, it is called Dido problem because the king which owned the land where Carthago was built, when Dido asked him, can we get a piece of land for building our small city? We need a small city for a harbor, simply for not having our sailors dying. The king answered her, yes, I will allow you to build a city on the area which you can cover with the skin of a cow. Okay, but Dido made a very small stripe out of a skin of a cow and encircled with a circle a big area, which was enough for building Carthago. So this is the mythology which transmitted us the fact that Hellenistic science knew the solution of the optimization problem of Dido. However, they did not have the rigorous proof. Otherwise, they would have written it together with the proof of the hexagonal shape. Okay. Very well. Now, with all these premises, these are motivations for justifying the intellectual effort which now I will require you. By the way, I will try to make intervals in our discussion because I understand that these are difficult concepts. So I will tell you some stories every more or less 10 minutes so that you can relax a little bit without losing contact with what I'm telling you. This is an old rhetorical trick. You know, people are tired. Okay, but if Bruno is tired in a different moment from Hevel, okay, what happens? That soon they will lose the logical flow of reasoning. If I stop in a certain moment, then everybody rests together, all rest together, and then I decrease the possibility of losing your attention, okay? Now, give me 10 minutes of your full attention, okay? We need real numbers, okay? If you have troubles with real numbers, go and read the book which Bruno suggested us, okay? Which, by the way, I suggested to Barchiesi, who suggested to José, and probably José suggested to Bruno. So this is a very good book. Everybody believes it is a very good book. Okay. Then we need R to the power n, which are the n tuples of real numbers. So I call this a generic n tuple of real numbers, Q1, Q2, Qn. Okay. Qi, where I goes from 1 to n, is a generic real variable. Okay. Okay. So we have a subset omega of Rn. Okay. And we assume that this subset is a set which is open. Okay. So what it means that a subset of Rn is open? Of course, I am drawing drawings in the plane, but you must make an effort to imagine this in n dimensions, which is not difficult. I will teach you a trick. You have one point in omega, small omega in capital omega. Then you can consider the ball of center omega and radius epsilon. Okay. So you have, what is the ball of center omega and radius epsilon? Is the set of points. Now we are calling Q1, Q2, Qn. So this n tuple I call Q without indices. So it is the set of Q belonging to Rn such that the distance between Q and omega is smaller than epsilon. This is the open ball. Okay. Now you can tell me, but I know the distance in the plane. I know the distance in the space. Which is the distance in Rn? The Euclidean distance in Rn is between two n tuples is. So it is better if we write dE, because in future we will invent different distances. The Euclidean distance in Rn between two entropoles x and y is the square root of the summation over from I from 1 to n of xi minus yi to the square, where x as component x1, xn, and y as component y1, yn. Okay. So we want that omega be an open set in the sense that every point in omega is surrounded by a sphere which belongs to omega. So a set is open when every point of the set is surrounded by an open ball. Okay, and this open ball is included in omega. So in formulas, for every omega belonging to capital omega, there exists a ball of center omega and radius epsilon such that B omega epsilon is included in omega. Okay, this notation is not invented for showing you, I'm not using it for showing you that I'm clever and exoteric like a Maya priest. Okay, this notation invented by Peano is the basis of the functioning of computers. Okay, and this is the notation of the calculus of propositions. Artificial intelligence is based on Peano's calculus of propositions. Okay, so omega is open if and only if this property is verified. Okay. Very often we will use the closure of an open set. Okay. Go in the book of basic advanced mathematics for finding these definitions, because you cannot live without, you know, civil engineering was invented by Cauchy. Cauchy was a civil engineer. Okay. Civil engineering has been the most mathematized theory in engineering for 100 years before electric and then electronic engineering were invented. Okay, so you should not believe that engineering is without mathematics. Engineering is based on mathematics. So don't be too much impatient and try to understand what is important. Okay, what is the closure of a set? A point in Rn belongs to a closure of omega if and only if for every ball having center x and radius epsilon, the ball has non-empty intersection with omega. Okay. So what it means, I have omega. Okay. I have a point here. This point is not in omega. Why? Because you can find a ball, you cannot find a ball which is included in omega, having it small radius. However, for every ball of center x and radius epsilon, the intersection between the ball and omega is non-empty. So close to every ball element of the closure of omega, you have always points of omega. Okay? Now, why I'm telling you this? Because mathematical analysis requires some properties of the sets where we are defining our functions. And very often we will need that in our mathematical model, the sets which we are using are the closure of an open set. Okay. Okay, now let's go back to the Lagrange way of reasoning. You have an important distinction now. We must understand something very, very carefully. You have a set of mathematical objects. And then you have the set of physical objects. Then you have also mathematical properties. And the set of physical properties. Okay? So just for reasoning, imagine to have the sun and the planets which are moving along around the sun. Okay. I don't see the Iranian students, but they promised me that they will discuss with Bruno and with other people about the standard treatment with Newtonian mechanics of the motion of the planets around the sun. If they're not doing it, Bruno, tell me, we will find a moment for giving you the material. But I think it is very useful if you collaborate. But you have an idea about that, okay? So you have the sun and the planets, okay? So these are physical objects, and we have the properties of these physical objects. You have the motion of planets around the sun. So you have all the relative positions, the fact that the moon sometimes is 1/2, 1/3, completely dark. Okay, these are the properties of the physical objects. And then we have some mathematical objects which are invented for describing in a simplified way the physical objects and their properties. So what we invented? We invented the concept of material particle. Okay. What is a material particle? It is a mathematical object. It is given a three-dimensional space, the Euclidean three-dimensional space, which is the mathematical model for the set of positions in the universe, okay, and given three axes forming a Cartesian basis of this, of the Euclidean space, you have the three coordinates of the point, okay? So every position is characterized by three coordinates, x1, x2, x3. Okay. Now, a material particle is a function which to every time instance t belonging to a time interval t0, t final, which is a subset of the set of real numbers, gives you the position x1t, x2t, x3t. This function is also called the motion of the material particle. Okay. Of course, if you start studying the motion of planets, you may immediately understand that you need to attribute a mass to the material particle. Okay. If you have a rocket and you want to describe its motion, for instance, a rocket starting from the Earth going towards the moon, okay, you can introduce the mathematical model of a material particle, but the mass of this object becomes a function of time, because the rocket is losing mass while it is progressing. Okay. Okay. So can we confuse the model material particle with the real physical object, solar system? We cannot, because in the mathematical model material particle, every planet has a position given by only one geometrical point. So in this mathematical model, you are not including some important, sometimes important features of the planets, their radius, so their overall dimensions, for instance. Okay. So what you are doing when you introduce a mathematical model of this kind, you decide, better, you conjecture that you can forecast the motion of planets simply knowing the position of one geometrical point, which we have called material geometrical moving point, which we have called material particle, for each planet. Okay. Is this conjecture true? The solution of Newton's problem of the motion of planets And the predictions which we have obtained out of this mathematical model tells us that this conjecture is correct. Wait a second. There are some motions of the Earth which are lasting millennia. These motions are the cause of glaciations, period. You know that scientists drilling in the Antarctica or studying some small animals, the shells of some animals, have proven that temperature on the Earth is varying in periods, okay? And there was a period in which 2/3 of the Earth were frozen, okay? They related these freezing periods with a very small variation of the trajectory of the Earth with respect to the Sun. In particular, in these moments, the Earth was going far from the Sun and less energy was transported in the Earth atmosphere by the sun rays. Okay. These motions are caused by gravitational interaction with other planets, but also by the friction of the oceans with respect to the Earth. So the Earth is attracted far, then you have some relenting of the speed of the Earth and it goes closer to the Sun. Okay. These small variations of the trajectory of the Earth around the Sun has the relevant effect in the onset of glaciations period. So why I'm telling you this? I'm telling you this for underlining that the physical objects and properties are different from the mathematical models, and the mathematical models can be applied only in particular specific instances. Okay. When your mathematical model is not predicting what is observed, then you know that you must either improve the model, so adding some details in the mathematical model, or if I must use here the technical epistemological word, if the falsification of the theory is very important, very serious. What is a falsification of a theory? Your theory predicts something and you go to verify experimentally your theory and you discover that the prediction is false. Then you say that you have a falsification of the theory. Okay. When your theory is falsified a lot, then you must change in a dramatic way the theory. You cannot simply add some extra details. Okay. Okay. Now, I hope you are ready to understand the difference between the concept of configuration and state. Configurations and state. You have a physical system. Okay. And it finds itself in time in different states. Okay. So the evolution of the phenomena in your physical system depend on the sequence of states in which the system finds itself. The mathematical model for the set of states of a physical system is called the space of configurations. So a configuration is a mathematical model for a state of a system. Okay. I will give you some different models using different configuration spaces for the same physical object, so that you understand that for the same physical object, you can introduce different spaces of configuration. Okay. Now, the idea of Lagrange, now we stop our epistemological considerations for a while, and we develop somehow the theory of Lagrange for spaces of configurations which are finite dimensional, or this is another word which is equivalent, discrete. Okay, so what I'm telling you now is not about physics. I am inventing a mathematical model. No, I am inventing a class of mathematical models. So I am developing the meta theory. Meta in Greek means beyond. So the theory which is beyond other theories, it is at the top of other theories. The meta theory due to Lagrange. So we start from an omega, which is an open set, an omega closure, which is the closure of an open set, subset of Rn. Okay. And we consider Q1, Qn, an element of Rn. When you are developing Lagrange theory, you call this Lagrange parameters. Okay. This is a configuration of your system. Okay. So we claim that in our model, we have a full description of the state of the system when we know its configuration. So the conjecture is the state of the system is sufficiently described when its configuration is given. Okay. So we say that in our generic system, we know enough about the system if the configuration is known. In the example of planets, the conjecture actually, we should not talk about Newton, but about Hipparchus, 2nd century before Christ, who is the man who described the motion of planets. But I will tell you more details about this later in the epistemological part of this course. So the conjecture by Hipparchus and Newton is the following. Give me the position of your planets. I write for you the gravitational interaction between the planets. I solve the ordinary differential equations of the motion of the planets, and I can forecast where a planet is in every subsequent instant. Okay? Now, if you want to study the alternance of seasons, this is not enough, because the Earth has an axis of rotation. And depending, which is not 90 degrees with respect of the plane of the elliptical trajectory. So in different moments of the motion around the sun, a different amount of energy arrives to the Earth. This means that a different amount of energy enters the atmosphere. And this means that you are in winter or in summer. So if you use the coordinates of the barycenters of the planets for describing the state of the system, you can predict many things. For instance, how much 1 year is lasting for the Earth, for Mars, for Jupiter. You can say where Jupiter is as seen from the Earth. So you can describe many phenomena, but you cannot describe every phenomenon. Okay. So how can we improve? The simplest way for improving is to include other parameters, other Lagrangian parameters for describing the state of the system with a richer space of configurations. Okay. Okay. This is the reason for which I must be abstract. So let Q1, Q2, Qn, and I will not tell you how big is n. I do not know how many parameters I may need for describing carefully enough a certain system. Okay, so let Q1, Q2, Qn. For instance, Professor Giorgio recently developed a model for a metamaterial in which n is 3 millions. Okay, because we needed to know in great detail the behavior of that piece of material. Okay, and we have proven that if you use less, you are in troubles. Okay, so be careful. This is not a mathematical twisted neurosis. I want to be general because I want to show to Bruno how clever I am. Okay, this is a true need from applications. Okay, so I must keep general. So I have n capital N Lagrangian parameters, and I call motion of the system a function phi, which maps a time instant in the time interval t0, t final, which has values phi t equal q1 of t, qn of t. Okay, in different situations, I will use q of t for meaning the n scalar functions which constitute the components of q. Each of these q1, q2, qn are these are the components. Okay, q represents the whole set of components. Okay, now I have a problem, which is the regularity we require to this function. Now, Newton, in my opinion, don't be upset. Don't believe that we spent 3 minutes because you must rest a little bit. So I tell you a story, which is, however, making you better aware of the situation. Most likely, this is not my opinion. This is Keynes, the famous economist. You know, the one who said what was going to happen if we give power too much to banks and we don't pay taxes. You know, Keynes is not a communist. He's a person who believes in capitalism, but he knows what wrong can happen if we don't establish rules for controlling economy. Okay, so this man was not understood fully, and the main reason, the reason of our actual problems, economical problems, is that we did not follow the theories of Keynes. Keynes studied history of science, and he has discovered that Newton was not so clever and so inventive as we believed. Actually, he had very good Greek books in his hands, understanding more or less in a good way, in a deep way, what in this book were written. In fact, Keynes calls Newton the last sorcerer. Okay, but we will come back to this. But now I want to tell you that Newton, reading some books, wrote Natura non facit saltus. Nature is not doing jumps. What it means? The function q of t is continuous. So this is a conjecture. It is not happening that a planet which is in a position at instant t, at instant t plus small, appears in another position. The plot of qi cannot be like that. Okay. Okay. I mean, do we believe that? Okay, I want to develop your criticism. Is this a truth? A physical truth? No. Okay. You will never be able to say if this jump is like that, or if this jump is like that. You cannot perceive. Our eyes are reading images every 1/10 of a second. So if the jump is quicker than 1/10 of a second, you see a jump, but instead in 1/10 of a second, you can have a continuous movement. Even the best camera which you have will have 10,000 hertz. I mean, there is always a discrete time of shooting the pictures, okay? So you can never say that this is a physical evidence, a truth which is proven, okay? This is a mathematical conjecture, okay? By the way, we are now talking via a computer, right? This computer is made with transistors, with chips. Do you know that chips are based on tunnel effect? Tunnel effect is an effect in quantum mechanics. You have a material particle here with an energy which is lower than the hill of potential, which I've drawn there. And this particle, 5% of times, jumps on the other side. In order to describe this phenomenon, which we are exploiting in our computers, natura facit saltus. Okay? So, what I want to say is that in our scheme, in our mathematical scheme, we assume that the motion is continuous. This is a conjecture. We will see if this mathematical assumption is well grounded or not at the end, when we have developed our theory and when we will know what our theory is forecasting. Okay, clear? Bruno, I see you a little bit confused. You agree with that? Okay. Now, not only we assume that q of t is C0. C0 means continuous function. We assume that q of t belongs to C2. Okay, you know that Newton mechanics is based on a fundamental concept which is called acceleration. And acceleration is the second derivative with respect to time of motion. Okay, so our conjecture, our basic conjecture is that Q of t belongs to the class C2, is 2 times differential. Now we are facing the main problem. How do we predict the motion of a given system? You know what we want to do? I will always remember a lecture of my professor of rational mechanics, which, by the way, was also my supervisor for master and PhD thesis. He said, we wrote the equations of Newton, okay? We solved them. We placed our telescopes and we found the planets exactly where we had predicted they had to be. Somebody may believe that this is magic. Okay. In civil engineering, we have similar things. The house of my mother has been built in Pozzuoli, a place where we have earthquakes every day. Okay. Our city is always trembling. Usually they are very small. So we are so accustomed that we even do not perceive them. Okay. But sometimes they are very heavy. Okay. There was a kind of natural selection of buildings. Those which were not strong enough, more or less were damaged. So we rebuilt them. But my mother was very worried. So she came to an engineer and she said, I want a building resisting to an earthquake of 8 Richter scale. By the way, in Italy, never it has been measured an earthquake 8 Richter scale. And in Pozzuoli, the maximum has been 5. Okay, but she wanted this so strong that she's anxious, okay? Then, during the construction, she changed only one wall. She moved a division wall of the bathroom. She wanted a bigger bathroom, okay? When we had an earthquake, this is prediction. When we had an earthquake, 4.3, very strong. My bed was moved from the wall 1.5 meters. I've seen the roof waving on my head. I was in my bed. Nothing happened everywhere in the house except in the wall moved by my mother. Okay? The comment of my father was, it's a pity that you were not under that wall that moment. Okay? So predictivity is the main feature of a scientific theory. Engineers are using scientific theories for predicting what happens. Of course, the theory of everything is not possible. So if in your simplification model, simplified model, you are missing something, it may happen that your prediction is not fulfilled. Okay, this is teaching you how to improve the quality of your model. Okay, now we stop 10 minutes. Ivan, please switch off the video. And